So thank you very much being here in the end of the day, and thank you very much for the organizer for inviting me to this great workshop. So I'm going to tell you about quantum enhanced multiparameter estimation and compressed sensing of a field. How does the light come out? Light is it? Yeah. Okay, thank you. So the work has been done by Youssef Bamara, who is a bright PhD student, soon finishing, Manuel Gessner, who was a postdoc in École Normale and who now is working with a permanent position in Spain, and myself. So I'm going to tell you about how to obtain quantum gain in multiparameter estimation in a simple way using spin squeeze states, and then show you some applications of this for sensing an extended field. Then I will briefly say how can one go beyond spin squeezing, meaning using over-squeezed states, more entangled states. And I also would like to spend 2 slides to tell you one way to obtain the kind of state we study, which is a state with the distributed entanglement that we want to use for sensing, and conclude. Okay, so the system we are considering is an arrangement, a regular arrangement of single 2-level atoms or single spin 1/2 that we want to use to sense locally the fields. So imagine, for example, so these balls represent our atoms. Imagine we prepare all these atoms, spin 1/2 pointing x, and then locally I have some magnetic field pointing z, and then those spins will precess by an angle which will be proportional to the field I want to measure, and so I can measure these angles which will encode the values of my field. So I have n atoms and n values of the field I want to measure, or phases, this precession phases theta I. The initial state, as I said, all the atoms are pointing x. This is a factorized state. Mathematically, the encoding of the parameters is described by this operator, which is just rotation with the generator SZ, rotation around SZ. So now the key point is that if I use single atoms and I will want to make this measurement to say to look at the precession, I will have a huge quantum noise. Imagine, for example, for one of them, one spin 1/2, I prepare it along x. Then I want to measure the precession. So if I measure along x, of course, I find 1/2 with no noise. But if I measure along y to see whether there was a precession in this state, I will find 0 on average, of course. But when I measure, I find plus or minus 1/2. And so there is a huge noise. This is the standard deviation 1/2. Of course, I can improve over this by repeating the measurement, because by repeating, the signal will build up linearly with the number of repetition, mu, while the noise will build up as a square root of mu, and so I gain, of course, by repetition with 1 over the number of measurements. But another way of gaining, in addition to repetition, is to create correlations in the ensemble, and this is the way I'm interested in. So first, let's see, we know already, but I recall you that one can gain in measuring one quantity, which is the spatial average of all the parameters. So imagine, for example, I have these spins, all are pointing x, but now I squeeze them. So I act with the famous one-axis twisting Hamiltonian we have been hearing a lot about. So the initial situation is depicted here. This is the Bloch sphere for the collective spin of length n/2. This is the coherent spin state pointing x with some noise. Then I squeeze it, which makes this noise circle and an ellipse, twist it. And then I can also, by single atom operation, put it vertical if I want it to be very sensitive to rotation around z, like this. And then I go with encoding my n phases, my n parameters. But then I measure a collective quantity. I measure just the collective component Sy of the spin, which is simply the sum of all the SY. And one can very easily see that this collective component is sensitive to one thing, that is the spatial average, that is the symmetric average, the sum just of all the parameters divided by n, simply because each spin gives me the local theta, and then I sum them, I find the sum of the theta. And by the fact that I have squeezed by reduced fluctuations in the collective component SZ, I can get quantum gain on this quantity, which is the spatial average. Okay, this is spin squeezing. Now, just a comment that here we look at this one quantity, which is the symmetric combination of all these phases. But this is also the one that is squeezed. That is, any other combination, any other orthogonal combination to this one in this squeeze state, which is made symmetrically by collective operator, will not be squeezed. On the contrary, will be we would have increased noise. Okay, so but now it's nice. I can measure the average, but I want each parameter, not only the average. And so what would be the way out? Well, okay, so I have to measure n independent linear combinations, and then I will inverse to get the values. And so I consider n independent linear combination of the parameters with coefficients which are actually plus or minus 1. And the idea is that this will be somehow easy to do in this way. That is, I imagine that I can perform local operations on these spins, although the measurements are collective. So if I perform a pi pulse before and after imprinting the phase on a particular spin, a rotation around x, this exactly amounts in switching the sign in front of that parameter. Then, if I measure the same thing as before, that is Sy, which makes the sum of all the parameters, I access another combination where I put a minus, and then I can put as many minus as I want. Okay, so, but now, by formalizing a little bit the thing, which are these combinations that I want to look at? These combinations are just the coefficients of the Walsh-Hadamard transform. That is, the relation which links the vector of the parameters to the vector of the combination is a matrix made of a plus and minus 1. And this matrix can be built in an iterative way very simply. So let's take, for example, the case of two atoms. It is a small n equal 1. I start with 1. I put it here. 1, 1, 1, minus 1. So the two combination in this case would be the sum of the two parameters and the difference of the two parameters. But then I can, for larger n, iterate. So I can take this 2 by 2 matrix and say same, 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 minus same, etc. And if I look at these coefficients, one are normalized, they are actually the Walsh-Hadamard functions that look like this. And actually they can be used as a basis of a discrete Fourier transform. And here you can already imagine what I mean by compressed sensing. But I will come back to it. Okay, so in this way, by measuring n independent combinations of the parameters, I can get, starting with the squeeze state, the same quantum gain for each of them, which will be given by the squeezing parameters. So this is a square root of the number of repetitions. It is each combination I measure mu time. And then the standard deviation I get on each parameter is 1 over square root mu with some quantum gain, which is simply given by the usual squeezing parameter of the initial state I have prepared. Okay, so now I just would like to give you some examples. So in the first two examples, we were doing as if we were experimentalists. So we just apply the protocol. So in this case, for example, we want to measure a scalar field. So we know the direction of the field, we just don't know the value, which is discretized over 8 sites. So we have 8 atoms. And then we measure, so we prepare the squeeze state, we do the flip, which select one Hadamard coefficient, and then we measure Sy a certain number of times Here mu is equal to 1000. And from the average, we estimate the coefficient with a calibration curve, which here is simply a linear curve given by the theory, which tells that Sy is simply proportional to the spatial average with the proportionality factor, which is the spin length. Okay, so we do this, we get the n independent, the n coefficients, we inverse to get all the coefficients, all the fields, and we repeat the procedure many times to get the error bars, which of course agree with the theory. So here we see the reconstructed signal, which was a sine, and the error bars for the coherence, sorry, the colors, they are not perfect. So the green is the coherent spin state case, and the red, the reduced one, is for the spin squeeze state. And here, the spin squeezing is not huge because we have only 8 atoms, and so the one-axis twisting cannot give more than some amount of squeezing. Now there is a question, what about if my field is not a scalar, is a vector? So I could have in my 8 sites some unknown direction, modulus and angle of the field. So what I say here is very simple. We don't want here to do fancy things like measuring at the same time the field in different directions. But what I'm saying is that we could show that what I just described to measure the component Z still holds in presence of the other components. That is, by selecting the initial direction of the spin and the component that I measure, I selectively choose, I'm sensitive only to one direction at a time. And so I can perform the measurement of the 3 components of the field subsequently. And here, I just give the example. We took, so 3 sinusoidal, just dephased. Along x is a sinus, the y is dephased by pi over 2, and then by pi in z. And we reconstruct, as I described before, and we find what is expect. Okay, so now more funny, since we are theorists, we go to larger systems. So now I have a scalar field which encodes an image that is a 2D arrangement. So I have 512 by 512 parameters and the same number of atoms. And I have a signal which is this one. And then I encode it via this unitary operation on my 2-level atoms here. And I measure the n Hadamard coefficients, all of them, repeating 10 times for each of them. And here, and then I reconstruct the signal, the image. And here I compare what I get with a coherent spin state here and with a spin squeeze state here. Of course, in this case, the gain is large because, as you know, if I perform the squeezing up to the optimal squeezing time, I get a gain which scales as 1 over n to the power 1/3. And here, since n is large, because it's 512 to the square, I have a gain which is large. What happens if the squeezing is not perfect? Of course, it will never be perfect. So here is just the same thing, but the squeeze state, the spin squeeze state we prepare, was prepared in presence of some dephasing process, in presence of the coherence, this collective dephasing process described here. In that case, the scaling of the squeezing is less favorable, 1 over n to the power 1/5, and the gain is smaller, but still you see a clear gain with respect to the coherent spin state. What about the compressed sensing? So the idea of the compressed sensing is that I was showing you these Hadamard functions. And so there is the one corresponding to the symmetric combination. The spatial average is flat. Then there is the one in which I have plus of them are +1 and then -1, etc., etc. And so they give you more and more rapidly varying spatial features. And so I can decide to measure only the first, for example, LH Hadamard coefficients. And so here, out of the 512 square, we measure only the 64 square first Hadamard functions. And we reconstruct the signal. So here is the coherent spin state reconstruction. This is with the perfect spin squeeze state, but with less coefficients measured. And this is with the imperfect spin squeeze state obtained in presence of the phasing I was showing before. And here I put the reference of the paper because I had some empty space, so you can take it if you want. It's open access. Okay, we also made some tests with a smaller sample. So we take just a detail here, about 1,000 atoms. So 32 square signal here. And we show that even with these small numbers, which would probably were more accessible to experiment, we can get a nice reconstruction. This is the reconstruction with 10 repetition for each coefficient with an imperfect squeeze state. And this is the coherent spin state for comparison. Okay, so now we can ask about the quantity we measured. We decided to measure this collective component of the spin Sy. Is this measurement optimal? What about the optimality of this measurement? So what I show here is the quantum gain as a function of time for an evolution of squeezing prepared with the one-axis twisting Hamiltonian here for 1,000 atoms. That is about the parameter similar to the previous figure I was showing, for about 1,000 atoms. So we have to keep in mind that in the end, the variance on the parameters estimation that we have will scale as 1 over number of repetition times this, the inverse of this quantum gain. And so here we have the green line here is the best we can possibly have, which is obtained from the Fisher information matrix for this multiparameter estimation process. And the yellow is what we have for our spin squeeze state. And we see that by measuring the collective operator as I was proposing, and we see that the procedure is almost optimal up to the best squeezing time. Of course, if we go longer than that, we go to over squeeze states. It means that the potential of a larger metrological improvement is there, but the measurement should be more complicated than simply measuring a linear component of the spin. And I will come back to this in 1 or 2 slides. And finally, this dashed line is what we have, what I call the imperfect squeeze case. That is when, while squeezing, we have some decoherence processes going on. So we see that this is far to be optimal, but still was giving us a nice gain. Okay, what about this over squeeze state? So now this time I'm showing here the whole Fisher information for this one-axis twisting evolution. It's a periodic evolution. So and this is divided by n squared. So the squeeze states are here in the beginning. And then what I call the squeeze and over squeeze states is all this family of states which are obtained for evolution time KIT. Chi is what is in front to the SZ square, which are in between 1 over n and 1 over square root n. These are states for which there is a mean spin, but they are squeezed, more and more squeezed. And then, so this is the Schrödinger cat. And in all this plateau already there is a Heisenberg scaling of the quantum gain. So I was saying that if you want to go to over squeeze state in general, you have to measure more complicated observable. And it was nicely shown by our Italian cohort, our Italian friends here, Luca and Augusto, that one should measure, for example, quadratic observables instead of quadratic. It means functions that are quadratic in the collective spin components instead of linear. And so what we were showing with Youssef and Manuel is that this echo technique, which we already discussed in some discussion in this workshop, allows, in fact, to do a simple measurement. That is, here the idea is that after squeezing, we squeeze here, we imprint the parameter, and then we act again with this one at one-axis twisting Hamiltonian with a different sign, and then we can measure a usual spin component, a usual component of the collective spin. So this eco technique that we call measurement after interaction technique, which was put forward in, for example, in this paper by Monica Schleyer-Smith in 2016. Actually, we give this point of view on this, that is as if we were measuring this nonlinear observable, because if you put here your simple component Sm, and then you sandwich with the state, you see that it's the same, that you are measuring in fact a nonlinear observable here, and we were showing that it corresponds to the best quadratic measurement and to the best nonlinear measurement. In fact, it gives the same scaling as the Fisher information for all these states. So it gives the optimal measurement for this whole class of states. And we were, in fact, the gain comes from the fact that this equivalent quantity that you measure is more sensitive to rotation. So in this calibration curve that I was showing before, it is steeper. And we were actually calculating the quantum gain with this technique, also in presence of different decoherence processes, and this is in these papers. So to finish, I want to show we can apply this to our multi-parameter estimation. So I go back to the simulation of the one-dimensional scalar field case. In this case, so we prepare the initial state, coherent spin state along X, we squeeze, we flip, we choose the combination by the flips, we imprint the phase, and then we go back with this anti-one-axis twisting, and we measure. And we see that we can get a small improvement. So the green is the coherent spin state, the yellow is the spin squeeze state, and the red is the measurement after interaction technique. Of course, the larger the number, the larger will be the difference between the squeezing and this other more advanced technique. Okay, and no, I'm not quite finished because I wanted to do yes, okay. Oh, great. So I wanted to just say a word about one way to produce this state I'm starting with. That is an arrangement of one single atom, and they are all squeezed. So a way, it's in fact to put together two techniques that have already been realized in experiments since several years. On one hand is the mode transition for a Bose-Einstein condensate in an optical lattice. And on the other hand is spin squeezing in two-component BEC. The idea is that in a two-component BEC, if you put all the atoms in a superposition of two internal states, for example, A and B, so your collective spin points X, you have atom-atom interactions which can give you, if they are not the same in the two states, they can give you this one-axis twisting Hamiltonian. And this was used to create spin squeezing, for example, in these two groups, Markus Oberthaler and Philipp Treutlein group. And so the idea is that we want to do this at the same time as the mode transition. I have another slide. And in the end, so we will get a compact arrangement of atoms in two internal states with the internal state coherence, so they will have an average collective spin, but they will have correlated fluctuations for the internal state. So this is the idea. You just start in a BEC in a shallow lattice in internal state A, and then you perform the Pio-2 pulse to put all the atoms in a superposition of A and B. And here, like Anna Maria, I go even further. It's really shallow lattice, meaning that it's in the superfluid phase. So the wave function is delocalized. Every atom sees every atom. No problem about this. And so the nice thing is that here we get all the power, all the strength is U. There is no small parameter. It's direct squeezing interaction. And then we adiabatically ramp the lattice such that we cross the mode transition at the best squeezing time. And at that point, we can freeze the correlations, because at the mode transition, then you have one atom per site. So you stop the dynamics there. and you freeze the state like that. And so we were studying this already since 2018 with some simulation using the Bose-Hubbard model in mean field, and then even exact simulation for small numbers. And we were showing that we can freeze like that spin squeeze state, but also more entangled state. For example, if we stop the dynamics, the one-axis 3C dynamic at the ket time, the bump up there, then we end up in a mod state, which is a superposition of all the atom pointing x plus all the atom pointing minus x. Okay, so this is the conclusions, and all the questions are welcome. Thank you.
Thank you, Alice. Well, Lorenza is fast.
I am very happy to see Walsh-Hadamard function coming in the picture. I have been using them for a long time. They have found application in quantum control, in decoupling, in frame theory, and also, so I have a comment and a question. The comment, we are office mates, so I can show you more on this. The comment is, I also think that the group of Paola Capellaro has used them for reconstructing the time-varying profile of a field. So I was wondering how this could be related and maybe cast in the formal setting of multiparameter estimation, because that's what it is in the end. And so I will share the references for what I know. That's the comment. My question is also, it seems to me that there could be analogies between, you want to construct another matrix for doing those tricks and getting a linear system of equation which is well conditioned, and then invert and do the estimation. We know from decoupling that there are, for instance, generalization to this function to 3 axes or more complicated combinatorial objects. So I was wondering whether this could also be ported in the field and help.
Well, I'm eager to learn, because actually we are absolutely beginner in this. We don't know, I don't know anything about, so I will be very happy to learn.
Will do.
So this is very basic.
I was totally unprepared to see
Thank you.
coming. So thank you.
Yeah, in terms of this Hadamard-Walsh transform, when you showed the 64 by 64 compression, how does it compare to traditional compression methods like PCA or something? Is it obvious you're getting the optimal compression modes, or with this particular transform?
Yes. So this, I don't know. I have no really background in image processing. I know it's a whole field, so I will be happy to discuss if you know more.
It just seems kind of, you didn't try to optimize it, you just applied this transform, right?
We just, yes, that is what was done, is that instead of measuring all the coefficients, we measure the coefficient corresponding to the first function, and we put the other to 0, and then we get the original n coefficients.
Thank you for a nice talk. I just have a question on multi-parameter sensing. So I'm not sure if I understand the scenario you described. Is it that you want to know, say, n different magnetic field felt by n atoms?
Yes.
Then if that's the case, how do you read out? Do you do collective readout?
Yes. So in what we imagine, we do only collective readout.
But then that's going to, because of the distribution of this magnetic field in this n atom ensemble, it's going to decohere your atoms, the collective spin. Because like each atom is rotating at a slight.
So when I measure a collective component, imagine I just measure the collective component. This is sensitive to the sum of all the fields. So it's the first information, the sum.
But you said that you are going to read out.
But then, so I want to measure n independent combinations. So the sum is a combination with plus, 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 plus. I measure other combinations and independent combinations, so that then I can inverse the result and go back to my original. And I want to do these collective measurements because I want to take advantage of the correlations among the atoms. If I would measure each one separately, then I will not be able to use the correlations.
Okay, I see. Thank you.
Yes, and Maria?
Thank you. Very, very nice talk. So I have a question about the mode insulator. So you start with, how sensitive is you? I'm confused. Is typically the spin squeezing is generated in the single mode approximation, but when you start to go too close to the mode insulator transition, you have many modes.
Actually, we did also exact simulations. That is, we start with the shallow lattice. The system is in the superfluid phase.
So all atoms in the zero momentum.
We take the ground state
Yes.
of the system, so it's not exactly all atoms in the zero momentum because there are some interaction, but almost.
Okay.
And then we ramp this lattice slowly. But in fact, what we were showing for large numbers is that if you take into account the time to squeeze, you have largely the time to squeeze is longer than the time to be adiabatic, so that there is in general no problem. So you ramp the lattice, and then what you see also by some analytics is that it's like if you have if you would have an effective time or an effective coupling which goes to zero when the atoms start to see each other. At some point you cross the transition, and then there is no evolution anymore.
And you record the 1/n to the 2/3 of the squeezing?
Sure.
Yes? Okay.
Yes.
Looking around, yes, please.
Thank you for the great talk. Just my question, just if I just got it right way, you just when you talk about just preparing, well, you have just some atom, just chain of atoms, and you squeeze each of spin. Yeah, that's you have just neighbor atoms have this one phase is plus, this another phase minus. So just that's so just
Actually,
if you can compensate, just
I
like
squeezed the ensemble, but this means if you only had two, it means that you would have anti-correlated.
yeah, anti-correlated phase. So
Yes.
just my question, just how just can do it? How just prepare that you phase just with anti-correlated pair?
This is so all spin squeezing protocols. So you have been hearing a certain number of them. I've been saying, but I did not explain. But I can explain you on the board. How does it go in Bose-Einstein condensate with atom-atom interaction? In general, to create these correlations among the fluctuation of the spin, you need either a nonlinear interaction or a measurement, or you need something. So what I was suggesting in this case, this work is done by the atom-atom interaction within the Bose-Einstein condensate. But there are many other ways. For example, they do it by letting all the atoms interact with one mode of the electromagnetic field in a cavity, for example, or measuring in a QND way the one collective component of the spin and measuring better than the standard quantum noise limit.
Oh, thank you.
Welcome.
So did I understand correctly? What you did in this reduction was just to take the longest wavelength parts of the Walsh-Hadamard
Yes.
component. So there was not a principal value analysis or what are the most important ones. It's a low pass filter or a high pass filter.
Exactly.
Yeah. Okay.
It's
super.
just if I was truncating a Fourier transform.
Yes. Super. No, so it shows there are not too many fine details in the picture.
Exactly.
Nice. Yeah. Okay, so fine, looking around. No more questions. Everybody is ready for the reception. Yes? Super, let's thank all the speakers of the session this afternoon.